station. So it's self-organized. Any self-organized network that I know of that's been analyzed exhibits small world properties. Human engineered networks typically do not. They typically are either lattice type or random type. They're not small world. Okay? What are the implications of this? Well, here's an example of the implications. I already mentioned local and global processing, regional specificity and distributed processing. They're ubiquitous among self-organized systems. The reason Watson-Strogatz were studying them is they thought that they might answer synchrony problems, and they do. It turns out small world networks synchronize very readily, whereas lattice networks will not. Random networks will synchronize as well, but they're not realistic. That was the problem with random networks. We can use them also to model and predict the behavior of important networks like the internet. So this network here, I show you as one of my fun networks. So it exhibits a lot of clustering. It has small world properties. It turns out what it is the 2009 Division I-A college football schedule. So I built this with one of my lab people I work with. We got the college football schedule, all right? And every team in the 1A conference, or the 1A, is in here. And then the lines represent games that they played with each other, okay? And so this kind of looks scattered and messy, but if you know anything about football and you start looking at this, you'll start to notice some things. What I did was I ran an algorithm that clusters this out based on interconnections between each other, all right? And I color-coded each of the neighborhoods. And so if you look at this graph, you'll notice that, for example, the blue dots over in the left bottom corner all have a similar relationship that you all might recognize. And that's the ACC conference. So it pulls out clustering by just simply what games were played. It has no other prior knowledge of this. And who knows football really well? Anyone? No one? Does anyone there know football really well? You guys are at Virginia Tech. Come on. No? There are 3 teams. This algorithm was able to identify every team 100% accurate except for 3 teams. And if you knew college football, you would know those 3 teams. So Army, Navy, and Notre Dame, because they don't belong to a conference. And so this shows actually Army here, Navy here, and Notre Dame right there. It stuck them in conferences because it didn't know they didn't belong. But nevertheless, otherwise, every color picks each conference perfectly well just based on what games they play, even though it's fully connected graph. So there's a fun thing, but you can imagine how you can use these tools on real networks to try and understand how things cluster apart, like biological networks. People are using it for protein networks. The folks up at the Ronalda campus do, to see what modules of proteins or enzymes function together and how they might cluster. All right, the other metric I'm going to talk about is degree. And that degree is simply the number of connections any one node has. And so on Facebook, you might have 1,000 friends. That's your degree. All right? Degree is important for many reasons, but I'm going to talk about one major reason. And it's about how it can determine the integrity of the network, okay? So we usually look at degree by the distribution because it turns out the distribution of degree is really interesting. It does not follow a normal distribution. It follows what's called a power law. And I don't know if you all study power laws a lot or not, but power laws are really interesting distributions. It's what's called the Matthew effect or the Pareto effect. Basically, 20% roughly of the nodes will garner over 80% of the connections. So this is a paper from Barabashi, published in 1999, the year after the Watson-Strogatz paper came out, where he described self-organized networks exhibit power law distributions. What this means is degree is on the x-axis, and essentially probability of connections on the y-axis. And what you see is most nodes have like 1 or 2 connections, and it doesn't matter if you're actors, the World Wide Web, or the power grid. But a few nodes have thousands. Well, in the World Wide Web example, a few nodes have nearly 10,000 connections. So they call these scale-free networks because there's no one scale of counting that captures all the nodes. Think of it like, I've had a hard time explaining this, but I think the best way to explain is, think of it like a measurement tool. If you're going to measure something that's microns apart, you're going to use a micrometer. You're not going to use a yardstick. So that would be on the scale of microns. It has a very special tool to measure it. This, there is no tool, essentially, because it spans many orders of magnitude. So you can have one connection or you can have a million connections, and there's no scale to it. That's what they mean by scale-free. The hubs turn out to be really important in this, and they turn out to really be critical for network integrity. So this is a plot from a paper I pulled showing how networks tolerate damage. And basically what you're seeing is tolerance on the x-axis. What that means by tolerance is essentially how much load any system's on. So if you took 1, that network is at full capacity. 100% of its capacity is being used. At 1.5, it has 50% reserve. You could add 50% more work to this network. Okay, does that make sense? All right. The y-axis is efficiency. Okay? And what these guys did was pluck out one node out of the network. They had networks with 10,000 nodes. One node they took out. And what they found was when the network's functioning at full capacity, one node has a tremendous effect on the efficiency of the system. But, and let me point out, random failure is the x. They randomly pick out a node, or is the square. The circles are targeting the highest functioning node, basically the one with the highest degree, okay? In a randomly generated network, there's very little difference between targeted attack and random failure. That once you're at about basically 1.05% capacity, you can tolerate removing a node. It doesn't matter. Take out a node, it doesn't affect you. Once you're at 10% reserve, for sure, you can take out a node, nothing happens, okay? If you look at a scale-free network, the behavior is very different. The random attack actually mirrors the random network very well. If you randomly take a node out of the random network, very little happens to it. And actually, I think I drew a line in here. Yeah. So notice the scales are slightly different. I don't know why they put slightly different scales, but if you draw a line down from the peak, they're basically actually the efficiency is almost exactly the same at the exact same tolerance. And as you get to 10% reserve, 1.1, they're both functioning full, no problem. Targeted attack is a very different story in the scale-free network. What they're doing is taking out the most connected node. And what it does is basically collapses the system. One node basically knocks this system down until you have nearly 35% reserve in the system. And it never gets back to its maximal amplitude. So even with the 50% reserve in the system, taking out one node, the most connected node, causes the system to basically fail. So what does that mean in the real world? Here's the power grid of the United States as imaged by a satellite photo at night, okay? And you can see the big cities and lots of energy being used. So what happens if you target one power line, one edge instead of a node, right? In Ohio in August of 2003. I don't know if anyone remembers what happens, but basically what happens if you take out one node that happens to have a heavy load on it, right? The load gets shifted, causes other nodes to fail. That shifts, causes other nodes to fail, and you get what's called a cascading failure. That is exactly what they measured here, cascading failure on these networks. This is the power grid, cascading failure on that day in which New York City or the whole Northeast was knocked out by what they tracked to one single power line going down. It was a hot day. Lots of energy is being used. That power line went down. It shifted energy to the other power lines, which were already running at capacity. They got overheated. They started to go out, and it basically cascaded, and you knocked out a tremendous